Jai Hind everyone. I, Suvarna Mujumdar, Assistant Professor in Electronics and Communication Department, welcomes you in a lecture on memory interfacing with 8085. Memory is a unit which we use with microprocessor to store the data as well as the program that we want microprocessor to execute. So how microprocessor can read or write a data from memory, how we can interface a memory with 8085 microprocessor, let's see in this lecture. So memory interfacing is nothing but how a microprocessor can frequently access a memory to read a instruction, that is the program or a code, and how it can store the data in that particular memory. For performing this operation, microprocessor has to perform two control instruction, that is machine control, memory read and memory write. When microprocessor is reading something from memory, then in that case read signal will be active low, and IO/M bar, this is the control signal which is active low, indicating that microprocessor is reading something from memory. If microprocessor has to write something, that is it has to store the result in the memory, again microprocessor has to select the particular memory and it has to make the signal active low, that is write signal. At the time microprocessor can either read a data from memory or it can write the data in the memory. So whenever microprocessor is performing any machine control instruction, that is reading or writing from memory, microprocessor has to generate these control signals. Now when this is occurring or when this is happening, first of all we have to make a hardware structure for that we have to make some interfacing signals, we have to connect hardware through hardware, we have to make the connection between memory and the microprocessor. Before that, just have a brief about memory. So memory is nothing but an array of a register. Each register has a unique address. So I can draw like this. This is if we consider this as a memory, then this is one register, second register, like this we have registers. So this register have a unique address. Now this register will consist of 8-bit data. So each memory will, if consist of an 8-bit data, then we can say that this memory has a size of n comma m, that is n comma 8 bit. Generally we have memory in the size of bytes, kilobyte, megabyte, gigabyte. In this we define the memory, the units we use. So this byte means a lowest unit, a lowest register will store a 8-bit data at one place. This is the two types of memory, that is the primary memory. We are not dealing here with the secondary memory. The primary memory, that we have two types of primary memory, one is RAM and one is ROM. When we say RAM, that is read write memory, where microprocessor can read as well as write the data. So the signals related to read write memory is write signal and read signal are the control signal. These are the address lines. So if I can say that A0 to A10, these are the lines, then in this memory, read write memory, we have 2048 different register. Each register is of 8-bit. And there is one input buffer where the data from microprocessor will be entering. And when microprocessor has to read something, this output buffer will be active by this read signal line, and the data will be placed on the data bus. In case microprocessor is dealing with EEPROM or ROM memory, EEPROM is the variant of ROM, that is electrically programmable ROM memory, read only memory. In this, code is already burned and we can only read the data from EEPROM. So there is only an output buffer, and to control this output buffer we will use read signal. If we are using more than one different types of memory, whether in our microprocessor, in our system, we have RAM also, we have EEPROM also, we have different types of memories on our kit system. Then in that case, which memory microprocessor is dealing with, which memory, whether EEPROM or whether it is reading or writing something from read write memory, it has to select this memory. So chip selection circuitry is also very important while dealing with memory interfacing. So we will see how we can design this chip selection circuitry to select different types of memory at a time. So the memory interfacing requires, first we have to select the chip. So we have to design a circuitry, a hardware circuitry, either using NAND gate or decoder logic to select a particular chip. If there is single chip, that if we have only using EEPROM or if we are using only read write memory, then in that case the single chip is selected and it will be always deal, microprocessor will always deal with this particular memory only. But if we have more than one memory, that is EEPROM and RAM, then in that case we have to select particular chip. So we have a unique address for that particular chip. After selecting the particular chip, that particular memory, we have to identify a particular register from where either we have to read the data or we have to write the data. And then we have to enable appropriate buffer, that is whether if we are reading something, then output buffer should be enabled. If we are writing something, then input buffer has to be enabled. So let's take an example. Here we are interfacing 1 kilobyte of memory chip with 8085 microprocessor. As we all are aware that 8085 has 16 address lines and 8 data lines. So 8085, by using 8085 maximum we can interface 2 raised to power 16 byte of memory. This is nothing but 64 kilobyte of memory. So this is the maximum capacity of 8085. So 8085 we can't exceed this limit as we have only 16 address lines and 8 data lines. So we can access at a time, we can read or write 8 bit of data. So in this example we have to interface only 1 kilobyte of memory. So first step, we have to calculate the address line required to address this memory location. So out of total 16 address lines, how many address lines we require to read or data, to select the data from this memory. So 1 kilobyte. So if I convert this 1 kilobyte, so 1 kilobyte, if I write it, it will be 2 raised to power 10 into 8. So 2 raised to power 10. So 10 will be the address lines. So to access 1 kilobyte of memory, we need 10 address lines. Like in first case, I told you that 8085 has 16 address line. So 2 raised to power 16 will be the memory capacity of 8085. So in reverse case, if I have a memory capacity, I can find how many address lines will be required to access 1 kilobyte of memory chip. So 10 address lines are required. So 8085 has 16 address line A15 to A0. So out of these 16 lines, only A0 to A9, 10 address will be connected with our memory. Rest of the lines A11 to A15 are used for chip selection. So for chip selection, we will use line from A11 to A15 and here we will use A0 to A9 lines. And the most important, we need signals, that is enable signal, output enable signal, read signal and write signal. So output enable is by IO/M bar. This signal we will use to enable the output. So this is the diagram where we can have the interfacing. So 8085 we have multiplex address and data lines. AD0 and AD7 lower order address lines are multiplexed with data lines. So we need a latch which can demultiplex higher or lower order address lines and data lines. So after latch we have separate address line and separate data lines. ALE, address latch enable signal. This signal is used to demultiplex higher lower order address and data lines. So this signal will enable the latch. So whenever we have to place address on address bus, ALE signal must be high, indicating that lower order address lines are carrying the address. Then we have to select this chip 1 milli. So we need to generate read signal and write signal. Read signal and write signal are generated with the combination of these three control signal, read, write. So we need NAND gate, and these are the active low signal. Memory read operation will be active low, memory write operation should be active low. So we are using NAND gate, two NAND gates, and the combination of these three signal will generate MEM R bar and MEM W. These two signals are connected to the read signal of memory chip. Okay, and A0 to A9, the address lines, 10 address lines of this memory is connected with 8 lines and 2 lines from higher order. Remaining lines A10 to A15, remaining 6 lines are connected for chip selection circuitry. Now here in chip selection circuitry, as we have only one memory we are connecting, so here we can use a NAND gate, or we can use a NOR gate because we are using universal gate, and we can connect this circuitry. So in second example, where we have to connect two memories, one is EEPROM, that is 1 kilobyte of memory, and second is 2 kilobyte of RAM. In this case, the question it is given that the address for 1 kilobyte of EEPROM is starting address is fixed 2000 and ending address is 23FF. Now in earlier version, we don't have, there is in question it is not mentioned about the address. So it's all depend on the designer who are making this hardware, whether it will go A10 to A15. The combination of this will make the address, generate the address. We will see how this address will be generated, but in this case the specific address is allocated to EEPROM, and we have to assign a new address of any choice to 2 kilobyte of RAM. So in case of RAM, we have address line A0 to A10, and EEPROM at is 1 kilobyte, the address 10 address lines are required. Here we required 11 address lines. Here we required 10 address lines. And we have output enable is similar to read signal, read bar. Output enable. Write signal, writing something in the memory. EEPROM does not have write signal because in EEPROM we will only read the data. Now as we have two memory chips, so we need a chip selection circuitry, and for that we use decoder. Or we can have a decoder to generate read write signal and IO/IO, because in the earlier version we have only one chip. In that case, we can only select that chip and we can perform the action. But when there are n number of chips, we need the required more decoder circuitry instead of NAND gate. Now in how we can calculate the address, starting address and ending address. So in case of EEPROM, the address, starting address is fixed 2000. Okay, so A0 to, it is 1 kilobyte, so up to A9, these 10 lines will be having varying value. Starting from 0, it will end to FF. The remaining lines 1, 2, 3, 4, 5, 6, remaining 6 lines, these are used for chip selection. And it is fixed that the starting address is 20. So 20 means 2000. So these are the nibbles, combination of 4 data. So this is 2, this is 0, this is 0, and this is again 0. In hexadecimal, we have a nibble combination, so 2000. So this will be the address. So in this case, what is the case? Here we are having A13 must be 1 for whole EEPROM access. So this case, the ending address will be 2. Now here we are having, this is a 2, 3. So 3, so in this case this is 3, 1, 1. 23FF. In case of RAM, it is up to us how we can define, but in case of RAM, the varying limit is A0 to A10. So we have to give address, there is chip selection with 5 this signal. So 5 signal, we have combination, 32 combinations are with us. Either we can have 00, we can have 001. So with this 5 bits, we can have 32 combination starting from 5 zeros to 5 ones. We can choose any of this combination. But in previous case, it expects that the first will be 20 and next will be 23. So from this, we will find the address and then we will connect the NAND gate accordingly. So remaining circuit is same. ALE latch is used to demultiplex lower order address line A0 to A7, and this will be our data bus D0 to D7. Higher order lines A8 to A15 are there. So in case RAM, we have A0 to A10. In case of EEPROM, it will be A0 to A9. Output enable, that is MEM read signal. So whenever microprocessor has to read something from EEPROM, it has to first place the address. So it will place the address 2000. This address will travel on the address bus. Read signal will be active low, indicating that microprocessor is reading something. So 2000 means this NAND gate will be active and this chip will get selected. In case microprocessor has sent an address 0007H, then in that case, this chip will be selected and data will be reading from RAM memory. Next example, here the EEPROM is of 16 kilobyte, and while designing the EEPROM 16 kilobyte, we have only 8 kilobyte of chip. Similarly, for RAM, we have to connect 8 kilobyte of RAM, but we have 4 kilobyte of chip available. So in case EEPROM, we require 2 EEPROM, each of 8 kilobyte, and in case of RAM, we require 2 RAM, 4 kilobyte each. Because available in the market, we have only 4 kilobyte of RAM and 8 kilobyte of EEPROM, but requirement is 16 kilobyte and 8 kilobyte. So we have to connect 2 each of 8 kilobyte. And here specifically 3:8 decoder is chosen. And we have to decide the address so that we can select a unique chip for data accessing. So in this case, we have defined a unique selection. So why not? That is A13, A14 and A15. Now for this, I can just, we will first define the address lines, required address lines to access. So to access 8 kilobyte, we need 2 raised to power 3 into 10 raised to power 10 into 8. So total 2 raised to power 13 into 8, we need 13 address lines. To access 4 kilobyte of memory, we need 2 raised to power 2, 2 raised to power 10 into 8, we need 12 address lines. So we are left with only 3 address lines. A0 to A11 and A0 to A12. So only A13, A14, A15. These are the 3 address lines are remaining. 13 are the we use 13, so 3 lines are remaining, A13, A14 and A15. These are the unique ILA. So combination of these 3 will be 0, 0 to 1, 1. So we have 8 combinations. Out of these 8 combinations, we can assign one combination to EEPROM, 2 EEPROMs. So 2 combination we assign to 2 EEPROMs and 2 combination we assign to 2 RAMs. So this will be the circuit diagram. We use 3:8 decoder, A13, A14 and A15. So 000 will be the starting address which will be used to select the first EEPROM. If we give 001, then in that case we will select second EEPROM. If we give 0, 1, 0, then in that case we will select RAM number 1, and if we give 0, 1, 1, we will select RAM number 2. Rest of the lines are common. And A13, A14, A15, A12, which is not used here, will be given as a NAND gate chip selection logic, because in case RAM is using only 11 lines, but we have to give address to all the 16 lines. So in that case, we have to use a one NAND gate for chip enable. So this is the circuit diagram for EEPROM. Here memory read and memory write, these two signals are generated and they are connected to write and output enable in case of RAM 1 and RAM 2, and memory write signal is connected with output enable lines. Here we can connect a latch also to distinguish between data and address lines and ALE signal. So this is the interfacing circuitry for 8085 with EEPROM. We have to interface input output device with microprocessor also. So there are two ways to interface these microprocessor with input output device. One is memory mapped IO configuration and another is standard IO mapped IO configuration or isolated IO mapped configuration. In case of memory mapped IO configuration, or we can say types, memory and IO device are treated as a same unit, and IO device are considered as one of the register in a memory. So out of these address, one address is assigned to the input device or output device. So for example, if we are connecting 4 input output devices with microprocessor, then in that case, out of 64 kilobyte of memory location, 4 location are allocated for input device and 4 location are allocated for output device. So we have lack of memory capacity. So the advantage what this is, the signal instruction that we are using for accessing memory, the same instruction will be used to access the input output device. We don't have to use different instruction in case we are using memory mapped IO scheme. In case of IO mapped IO, we have separate address space and we have separate address instructions to access the input output device. So in case of 8085 microprocessor, we have 255 or we can say 256, we can connect 256 input output devices in IO mapped IO configuration. So we can have 256 IO and we have separate 64 kilobyte of memory. So if we need a long code to write, then in that case we will prefer IO mapped IO scheme and we will connect at maximum 256 input output device. But the disadvantage is that we have to use different instruction, that is in and out are the two instruction that we are going to use while accessing this input output device separately. So in recap session, we will going to discuss whatever topics we have covered. So we discuss about the memory. There are two types of memory, primary memory that we are dealing with. One is RAM, known as read-write memory, and one other one is ROM, where we can have EEPROM or EEPROM. So whenever we have to connect microprocessor with some interfacing, that is memory, so that microprocessor read or write the data as well as code from this memory, we have to first make the address line selection. How many address lines are required to access a particular memory? So first of all, we have to find the number of address lines required. In case of 8085, we can't exceed a memory capacity by 64 kilobyte. So the combination of RAM or ROM must be live within the 64 kilobyte, that is 16 address lines. So first of all, we have to find the number of address lines required to access a particular memory. Then the next is we have to decide the chip selection circuitry. So in case of chip selection circuitry, again we have two types. One, either we can go with NAND logic, that is NAND circuits, we can use NAND gates, or if we have more than one or more than two memories, if we have 2 RAM, 2 EEPROM or 3 RAM, we have different combination, then in that case mostly we can prefer decoder logic, so that our PCB, that the board, that circuit we are going to design hardware, that circuitry will be less complex. Because if we go with NAND logic, then we require NAND gates separately for each of the RAM or EEPROM. So if we have 5 memories to be connected, then we require 5 NAND gate. Instead of 5, we can go with the decoder. Mostly we can use 3:8 decoder. We can connect 8 memories with this 3:8 decoder with a unique address. Either the address is given to you, a specific address for a specific memory, or as a designer or programmer, we have to select that which memory has a starting address and its ending address. So depending on the capacity, the ending address will be decided, but starting address will be decided either by the designer. It all depends on the designer how it will choose that starting address. So starting address will be from 000 in case of microprocessor 8085, and ending address will be FFF if it is totally using 164 kilobyte of memory. But if memory is having 1 kilobyte or 2 kilobyte, the combination is different. Then it all depends on the designer how it can design the selection address to the assign address to RAM or EEPROM. Next is the buffer. So in case of RAM, we have two buffers, input buffer and output buffer. In case of EEPROM, we have only the output buffer because we are reading the data from this memory. So we have to select the buffer. So in case of input buffer, we are going to select write memory, write signal. We have to output the data, so we can use read signal. So now we have to connect these read and write signal with the memory also. Again we need some logic, that is NAND logic. We are preferring to connect this input output buffer and selecting these input output buffer after selecting the chip selection. So how microprocessor will work when we connect all these hardware? Microprocessor first send address on the address bus. ALE address/enable signal will be high. This address which is sent on higher order address line. These higher order address lines mostly used for chip selection logic, and the particular chip is selected. Once particular chip is selected, after that read signal or write signal will be active and active low, and microprocessor can read the data from that particular IC. The same process we can use with 8085 microprocessor if we have to interface the memory, and if we are dealing with a microcontroller, and in case of microcontroller, if our program is larger than the input memory, then in that case we have to connect the external memory with the microcontroller. So interfacing of external memory with microcontroller, same logic, same process we are to follow, and we can connect the external memory with the microprocessor. So in case of 8086 microprocessor, we have 20 address lines. So the maximum capacity of this 8086 will be 1 megabyte of memory. So we can have different combination of memory. But in case of 8086, the small difference between 8085 and 8086 is here, that 8086 has 16 data lines. So at a time, this processor needs 16-bit of data. But as I told you, we have a memory mostly with 8-bit memory, 8-bit data in a one register. So here in case of 8086, the addresses scheme is having, we have two type of memory. So one we can say as even bank, and one we use as a odd bank concept. So in case of even bank and odd bank, at a time microprocessor can read from both the data, both the memory, and 16-bit data is available for 8086 for processing. So microprocessor will use for if microprocessor 8086 required only 8-bit of data, then it will read the data from even bank. So The address for this even bank will be even, that is 00. Next address will be 002, like this. In case of odd bank, the first address will be 001, like this. So we have two banks of memory, and microprocessor can deal with these two memory bank, and we have a combination of BHE signal, A0 signal. These two signals are used to read the data either from even bank or odd bank. So in case of 8086, rest of the logic is same, but we need to have two banks accessing so that we can read at a time 16 bit of data lines, 16 bit of data from a memory. Thank you.